Hello friends to my channel. Now on yesterday's lecture I have told about the motion of a body falling through a viscous medium, and we see that after a particular time when a body falls through a viscous medium, as time increases the body attains a constant velocity known as the terminal velocity. That we know. Now in today's lecture we shall going to discuss an important topic, that is Stokes law. Stokes law. Okay. Now what does this law states? That we all know that when an object or when a body passes through a medium, okay, when an object or when a body passes through a medium, the medium opposes the motion of the object, okay, and this opposing force, that is the viscous force, can be expressed in terms of Stokes law. Okay, when an object or a body passes through a medium, the medium offers a dragging force to the motion of the object, and this viscous dragging force is usually expressed in terms of Stokes law. Okay, now this law states that if an object of radius r is moving slowly through a homogeneous viscous liquid of viscosity eta, then the viscous force exerted upon the sphere is this 6 pi eta r. Okay, and when an solid object is moving slowly through a homogeneous viscous liquid with a velocity v, okay, then the viscous force exerted upon the sphere is 6 by eta r, where v is the velocity of the object, r is the radius of the object, and eta is the coefficient of viscosity. Okay, v velocity of the object, r radius of the object, and eta viscosity coefficient. Okay, that whenever a small sphere, you can say a small sphere, is passing through a homogeneous viscous liquid with a velocity v, then the viscous force exerted upon the sphere is 6 by eta r. Okay, so this is the Stokes law. Okay, that is, this is the viscous force offered by the medium to the motion of the body. Okay, now let us check whether this law is right or wrong. That means whether the formula is correct or not. Here we use the method of dimensional analysis. Okay, by the method of dimension, by the method of dimension. Now we see that viscous force depends upon which factors? Eta r v. Say eta to the power x, r to the power y, and v to the power z. Okay, now we have to write this in terms of dimension. Now what is the dimension of force? mlt to the power minus 2. Okay, and what is the dimension of eta? We all know ml to the power minus 1, t to the power minus 1. And what is the dimension of r? That is length. And what is the dimension of v? lt to the power minus 1. Okay, so this is simply m to the power x, l to the power minus x plus y plus z, and t to the power minus x minus z. Okay, now if we compare both sides, if we compare the indices in both sides, then we get x equals to 1, and x plus z, this is equals to 2, that means z equals to 2 minus 1, that is 1. Okay, and minus x plus y plus z, this equals to 1. So So what will be y? Y will be 1 plus x minus z. So what is x? That is 1, and what is z? Minus 1. So ultimately we get 1. So after solving, we will find that all the values are 1. X, y, z all are equal to 1. Now if we substitute the values, then what we get? If we substitute the values, that is, this is x1, y1 and v1. Okay, so clearly we see that the viscous force depends upon the viscosity coefficient, radius of the sphere, that is the radius of the object, which we usually take a small sphere, and velocity of the sphere. Okay, now by the experimentally it has been found that the constant k is equal to 6 pi. Okay, experimentally it has been found that the constant k is equal to 6 pi. Experimentally it has been found that the constant k is equal to 6 pi. So what will be my f? This is equals to 6 pi eta r v. Okay, f equals to 6 pi eta r v. So this is the Stokes law. Thus we see that the formula is correct. Okay, now one thing we have to discuss, that how this law can be used to find out the viscosity of more viscous liquids. Okay, how Stokes law can be utilized to find out the viscosity of more viscous liquids. Okay, suppose this is the liquid medium. Okay, and the object falls in this direction, say with a velocity v. Okay, now if rho is the density of the object, okay, rho is the density of the object and r is the radius. Okay, so what should be the own weight of the sphere? Weight of the sphere, this is simply 4/3 pi r cube rho g. So this is the weight of the sphere. Now when it falls through the liquid again exerts an opposite force. Okay, so if sigma is the density of the liquid, if sigma is the density of the liquid, so what will be the upward force? Okay, or you can say the upward thrust. What should be the upward thrust? This is 4/3 simply pi r cube sigma g. Okay, when it falls through the liquid exerts an upward force, and if sigma is the density of the liquid, so then this is the upward thrust. So what will be their resultant? Their resultant is this minus this. Okay, so if we subtract this from this, then what we get? This is 4/3 pi r cube g into rho minus sigma. Okay, now again the viscous force opposes the motion of the object. That means the viscous force acts in the opposite direction of the flow of the object. That means the object is falling in this direction, so the viscous force will act in this direction. Okay, and we see the resultant of these two forces is this. That means this resultant force is balanced by this viscous force in equilibrium condition. Okay, in equilibrium condition, this resultant gravitational force is balanced by the viscous force. Okay. In equilibrium, the net downward force is balanced by the viscous force, that is 4/3 pi r cube g into rho minus sigma. This must be equal to 6 pi eta r v, and from which we can easily write eta as 2/9 r square g rho minus sigma by. Okay, the marker is almost end. Okay, so I have to buy a new one. So this is the formula. Eta is equals to 2/9 r square g rho minus sigma by v. So this formula is used to find out the viscosity of more viscous liquid. Okay, so this formula is utilized in order to find the viscosity of viscous liquids. Net gravitational force is balanced by the viscous force. So dear guys, if you like this video, then kindly subscribe my YouTube channel. Okay, thank you.